So just to sort of reiterate some of the stuff that was in that chapter or that lecture, we were in chapter 7 basically. And in chapter 7, we're really talking about types of reactions and really different ways to classify reaction. And as I mentioned in that recording and that lecture, there's really sort of two reactions that you come across, and those are double displacement reactions. And double displacement reactions essentially can be identified by really what you're starting with. And in that case, you're going to always sort of start with two ionic compounds. So you'll have a positive guy and a negative guy, a cation and anion. And always when you have two ionic compounds like this in a double displacement reaction, what happens is really the two positive guys switch partners basically. And when they switch partners on the other side, they will form obviously two new ionic compounds. And double displacement reactions are really responsible for, in essence, two of the three reaction will take place, or why a reaction will take place, is as a result of this sort of exchange here, you will form some type of solid, which is a precipitation reaction. The other sort of thing that will happen in a double displacement reaction is maybe one of these guys form water, and the formation of water is kind of the second reason why a reaction will take place. And typically acid base reactions, as we'll talk a little bit more about today, are typically the ones that will form water. So out of the three reasons that you could pretty much identify for any reaction taking place, solid or water being formed, they fall under sort of the double displacement umbrella. As we will see also a little bit later on here today, underneath that umbrella, you can more specifically classify in other ways, but at the core of what's happening is still this sort of double displacement reaction. On the other side of like the big sort of umbrella of reactions are what are referred to as redox reactions. And redox reactions are oxidation and reduction reactions that occur. And redox reactions basically take care of really the third reason why a reaction might take place, which is a transfer of electrons. So those three things, electrons being transferred, the formation of a solid, or the formation of water, pretty much every single reaction that you see will boil down to basically one of those things happening. And that is basically the three reasons why it takes place. Now, in the first part of that lecture, we talked about double displacement reactions and really precipitation reactions, which is the formation result of a double displacement reaction. And we also talked about sort of three important types, right, as a result of sort of double displacement reactions. So if we took something like silver nitrate, which is a solution, and some sodium chloride, which is also a solution. Once again, when we have this sort of setup here, we could identify this as a ionic compound, so positive, negative, positive, negative. So right there, you know it's going to be sort of a double displacement reaction where the up with the negative hook up over here. It is important that when you do write the formulas on the right-hand side of the equation, as was also sort of mentioned, you want to make sure that you always sort of put the formulas first and then balance the equation. Again, you don't want to try to do those things together, otherwise you'll get the wrong formulas and the equation will not balance. So ultimately here, we have silver that's going to end up with the chloride, and we will have the sodium that will end up with the nitrate. Now, the reason we end up with these formulas without the negative there is because ultimately what makes up silver nitrate is a silver ion and a nitrate ion. What makes up sodium chloride is a sodium ion and a chloride ion. So again, when we put these together, just like in nomenclature, we just want to equal it to 0. So we just need one of each. Same thing here. When we put these guys together, we just need one of each of them to get the proper formulas. Now, once we have it, we could balance the equation with coefficients. And in this particular case, it is actually balanced. We could also determine, which is something else mentioned in there, whether or not we would expect maybe a solid to form or a no solid to form if we sort of put ions together. And those are really the sort of solubility rules that was shown in that video. And again, just to take a look at them here together, there are certain things that are soluble in all cases. And if something is soluble, those are the guys that get the aqueous symbol. And basically means that it's going to be a solution. So no solid's going to form. You're just going to have things floating around, ions basically floating around in that solution. So anything that has group 1 in it will be soluble. There's no exceptions. Anything with ammonium or anything that contains nitrate, chlorate, or perchlorate will be soluble no matter what the situation is. Now, there are certain things that are soluble, but there are some exceptions. So, for example, things with chloride, bromide, and iodine are normally soluble, which means they normally would get the aqueous symbol. But there are 3 exceptions, and that is if any of those guys are hooked up with silver, lead, or mercury, then it goes from being soluble to being insoluble. And things that are insoluble get the solid symbol, and you would expect them to come together to make some type of precipitate or solid and basically come out of solution as are soluble except for calcium, silver, which are slightly, and barium, mercury, tin, and lead, which are insoluble. Now, there are things that are typically insoluble. So hydroxides are typically insoluble, which means they typically get the solid symbol, except if they are with group 1 or ammonia. And that is pretty much where a lot of our strong bases come from, like sodium hydroxide, potassium hydroxide. So those guys are typically soluble and solutions. Carbonates, phosphates, and sulfides are typically solids, except when they're with group 1 or ammonium. So typically these guys will be solids, except if they are with group 1. And then they would be aqueous. So there are some exceptions. So if we sort of go back to that equation that I just wrote there on the previous page where we had silver nitrate plus sodium chloride goes to silver chloride and sodium nitrate. We could use these rules once again to determine the solubility. So when we look at the first one, we may not see silver by itself, but we do see nitrate. And when we come up here, nitrate is pretty much soluble in everything. So there are no exceptions. So we would expect this guy to be a solution and be aqueous. Same thing here when we go to the sodium chloride. As soon as we really see sodium, you don't really need to look any further. That thing's going to be soluble no matter what the situation is. So it will be aqueous here. You could also look at the chloride. In this case, the chloride would also be soluble. The only exception is silver, lead, or mercury. And in this case, it's sodium, so it should be soluble in that case. Now, when we come to the chloride over here, though, that chloride is hooked up with an exception, which means instead of normally being soluble, it will now become insoluble. And this would be the white solid that we would expect to form when you mix these 2 things together. And over here, we see everything, soluble in everything. So either one of those will lead you to it having the aqueous sort of symbol. Any questions on how to use that there? So this equation, what is referred to obviously as the molecular equation, where we write everything out in their proper formulas. But we could also, again, write another equation which basically describes what's happening when we mix those 2 solutions. So really, when we mix this solution with this solution, what happens is they are strong electrolytes, which means they are going to completely break apart into the ions that are present. And basically, we got these ions floating around in the solution at this point. So when we which most ionic compounds are. That means that they will 100% break apart in solution. You'll have none of the whole unit still together. So completely broken apart, pretty much just ions floating around in solution. Stay together in solution and break apart. In this case, we could write another equation where our silver nitrate would break apart into ions in solution. And we would have a silver ion and a nitrate ion. We would also have our sodium chloride break apart into a sodium ion and a chloride ion. Now, our silver chloride in this case will stay together because it is a solid, and anything that's a solid, a liquid, a gas, or anything that's a weak electrolyte, you typically will keep together in this type of equation. And our sodium nitrate will break apart into a sodium ion and a nitrate ion. And this equation here, which really describes sort of what is going on in that beaker when you mix these things together, is what is sometimes referred to as the total ionic equation, or complete ionic equation, or just ionic equation. Now, when you write a total ionic equation, you should be able to find ions on both sides of the arrow, which look exactly the same. So in this case, we do have nitrate on the left and nitrate on the right, and we do have sodium on the left and sodium on the right. Now, these ions that you can find on both sides of the arrows here, they are what are referred to as being spectator ions. And these are spectator ions. And spectator ions, much like the name implies, are things that are basically just hanging out, not doing much. They're just watching. They are not leading to any sort of product being formed in this reaction. They're just there really to balance charge. They're frankly still floating around the solution part of the whole beaker there. And what we typically do with spectator ions, because you should have the exact same number of these ions on both sides of the arrow, they will cancel out. And this will leave a third type of equation, which is an important one. And this equation really tells us what is happening when we do this reaction. It is really the silver ion from the silver nitrate is going to float around there and find the chloride ion that's floating around. And they're going to come together and make this solid silver chloride. And this is what is referred to as the net ionic equation. So basically, these two guys are going to come together as they're floating around and make a solid. It's actually a white solid, but we'll draw it with a different color here. And again, that sodium ion and that nitrate ion that are spectator ions, much like in my picture, are really just still floating around in the solution, not making any product. So when we do this reaction, this is a precipitation reaction because we did make a solid, which is the sodium chloride. I'm sorry, the silver chloride. And we can write this sort of net ionic equation, which basically describes what's going on here. And it is one of the three reasons why a reaction takes place is that formation of a solid here. So ultimately what is happening here is we're making a solid, and that's really the reason why this reaction is taking place. Any questions on that there? So that was a little bit what was covered there in the first little bit of this lecture. And again, make sure you do watch it if you have not done so. Like everything else at the school, they'd expect you to know the solubility rules, so they will not be provided for you. So do make sure that you do know them. Any questions on any of that there? Again, as we will see, a precipitation reaction that we're talking about here is a really more specific classification of a double displacement reaction. The other, which is what happens when we take acids and bases together. So these type of reactions as well are going to kind of fall under that double displacement category. And what happens when we take an acid and a base together, pretty much this, whenever we take like a strong acid and a strong base together, or really almost any acid and base combination, usually will always result in sort of two things. It will result in a salt and water. Water obviously is H2O, and a salt is an ionic compound. And as we will see and talk about, and as you can kind of see there, this is again another reason why a reaction takes place, which is the formation of water. And again, a salt is just an ionic compound. It's really made out of, for the most part, the spectator ions that are floating around in the solution, a positive and negative guy coming together. So let's talk a little bit about basics, about what each of these things are, some characteristics of it. An acid has a sour taste. If you use litmus paper, it will turn the litmus paper red. So if you take a solution and you dip it on a piece of litmus paper, and it turns red, that means that that solution is acidic. It will react with certain metals to produce hydrogen gas, which I think we've done somewhere along the way, or you did somewhere along the way where you put some zinc and some hydrochloric acid in a test tube. You put your finger over it, I think, right? And popping sound with the lighted splint. That's going to produce hydrogen gas in a reaction, as we'll talk about today, which is really a single replacement reaction. Aqueous acids are also can conduct electricity. So acids are electrolytes, and both of those things can conduct electricity. Bases, on the other hand, have a bitter taste. They feel very slippery. Most soaps, like drain cleaners, that type of stuff, are bases. They also will change litmus paper, but they will turn it basically blue. So if you hit a piece of litmus paper with a solution and it turns blue, that means that that solution is actually basic. They also have strong bases and weak bases, which both are electrolytes and both can presence of ions. And again, that is what makes something a good electrolyte, is really the presence of ions. And the presence of those ions is what helps it conduct electricity. So an acid is something that really has the ability to, in solution, H plus, which are sometimes referred to as protons. When you're dealing with acid-base chemistry, you will see H plus and you will see H3O plus, which is the hydronium ion, used sort of interchangeably. So if you see H plus or you see H3O plus, it's pretty much an acid, and it's talking about an acidic sort of solution because of it. They will also call sometimes H plus a proton, and that is because a hydrogen has one proton and one electron and no neutrons. In order for it to become positively charged, it had to lose electrons, so that leaves it just a proton. So sometimes H plus is called the hydrogen ion, H plus is sometimes called a proton, and sometimes people use H3O plus instead of H plus, and they're all really referring to the same thing when you're talking about acids and bases, to really the acidic part of the solution. Now, when we talk about something producing this, what we are talking about is the ability to, in a solution, basically produce free H pluses basically floating around. So the ability to produce just a bunch of free H pluses floating around freely in that solution is what we're talking about, is the ability of it to be an acid. Now, there are some strong acids, which are strong electrolytes, which means that they will 100% break apart in solution. Something like hydrochloric acid, when it is in solution, it will 100% break apart into H plus and Cl minus. So 100% of what you would have in that like beaker would be H pluses and Cl minuses. You would have none of the HCl unit together. That would be all that you would have in there. And because, as you can see here, that would produce a lot of free H plus floating around in the solution, it's a strong acid because of that. It just pretty much needs to go for a swim, and it's going to produce a bunch of free H plus really quickly in that solution, and thus it's going to become probably pretty acidic, that solution, because of the of those H pluses basically going around. Now, any strong acid like that will do that. If you had nitric acid, which is HNO3, you would have 100% H pluses and 100% nitrates floating around in that solution. It's a good idea to know some of the strong acids, and just to make a little list here, hydrochloric acid, nitric acid, perchloric acid, hydrobromic acid, hydroiodic acid, and sulfuric acid. I would say these 6 here are really good ones to commit to memory as you go through your chemistry career here, because those are pretty much your 6 strong acids that you're going to come across. The reason why it's good to remember these 6 is if it's not one of those acids, it's probably a pretty safe bet that's going to be more of a weak acid. So if it's not one of these 6, then it's probably, like I said, a pretty safe call to think that it's going to be a weak acid. So what is the difference between, again, a sort of strong acid and a weak acid? A weak acid is a weak electrolyte. So something like hydrofluoric acid, when it goes for a little swim, will also break apart a little bit into H plus and F minus. The main difference, though, is in that solution, you will actually mainly have the whole thing sealed together. So if you were to look at that, you would mainly have in this solution a bunch of HFs floating around, and you have a little bit of some H plus and F minus floating around. So because it's still able to produce some H plus in solution, it's still considered an acid, but it will not produce anywhere near the amount of H plus as something that's a strong acid will do. And again, that's why obviously the HCl is much stronger of an acid. We also saw those arrows heading in both directions, which is typically what you see with a weak electrolyte. It will mainly stay together rather than break apart. Strong electrolyte or strong acid or base side together. Questions on that there? Now, bases, on the other hand, bases are something that has the ability to produce hydroxide in solution. And what we're talking about here is much like the acid, something that has the ability to produce free OH minuses floating around in solution, but kind of freely floating in that solution. A lot of strong bases come from group 1 and group 2 on the periodic table and have actually hydroxide in the formula. Hydroxide, potassium hydroxide in a beaker or solution of sodium hydroxide. Because it is a strong base, you would have only sodium ions floating around, and you would have a bunch of hydroxide ions floating around. And again, that production of a bunch of OH minuses really quickly is what makes it a strong base. I would say if you look at the periodic table right around lithium, and then you come down to sodium, to potassium, hang a right, and over to calcium, strontium, barium, all these guys with hydroxide are typically where your strong bases are found. So a lot of those guys are your strong bases. Again, group 1 is the alkali metals, group 2 is the alkaline earth metals, and the word alkaline bases come from in solution. Now there are weak, the most common weak base that you would come across, and there are others obviously, but ammonia is actually the very common weak base that we do see a lot. And what happens with ammonia is ammonia would need to, go find himself a water. And what's going to happen is the ammonia is actually going to grab off an H plus from water. The result of that is it will make NH4 plus and some hydroxide there. And again, because it's able to make that hydroxide, it is considered a base. The difference is, again, between, say, sodium hydroxide and that is, you would probably mainly have a lot more ammonia in the solution and a little less hydroxide kind of broken apart. So a lot less of that hydroxide is going to be made. And that's because really ammonia's got to go find water, do a little reaction to produce the hydroxide. You could think of like our strong bases, they're carrying the hydroxide with them. So as soon as they go in, they're just going to let it go, and it's going to be produced really, really quickly. So there's a major difference between those two. Any questions on that? So as I mentioned before, when we do react strong acid and a strong base. Pretty much what's occurring is that formation of water, which, as I mentioned a number of times, is again one of the three reasons why it takes place. So if we look at any sort of combination of that, our hydrochloric acid and our sodium hydroxide. And again, as we saw there, we'll make a little sodium chloride and some water here. And again, this is still a double displacement reaction, positive, negative. These guys are going to come together, and these guys here are going to come together. Pretty much in any sort of acid base, strong acid, strong base, we will make, as I mentioned, this is our salt, which is our ionic compound, our sodium chloride, and this obviously is our water. Pretty much in this type of reaction, the H from the acid and the OH from the strong base, that is where you're going to generate your water from always. So that's pretty much where the water comes from. And what's left over when you do that is pretty much where the salt part comes from, which is the sodium and the chloride going to come together here to make our sodium chloride. So this is a double displacement reaction. This is more specifically called a acid-base reaction. And we could also write, in addition to our molecular equation here, we could write H plus, as that is a strong acid. We'll break apart into H plus and Cl minus. Our sodium hydroxide, which is a strong base, will also break apart into its ions. Our salt here will be broken apart. And our water here, which is a pure liquid, will stay together. So this again is our total ionic equation, our complete ionic equation. And again, it really describes what's happening when you dump both of those things, say, into a beaker. That HCl will break apart into H plus and Cl minus, the sodium hydroxide into these two guys. And ultimately here, what we see is we can find ions, and our spectator ions here are going to be the same ions on both sides, which would be the chloride and the sodium. And again, if we cancel them out, our net ionic equation, which is basically that H plus from the acid, we'll go and find that OH minus from the base, which they have a very strong affinity for each other, and we will make water. So ultimately what's going to happen there is those two guys are going to come together to make water. The other two ions are just going to be floating around still in that water solution. Unlike a precipitation reaction where you could actually visually see, right, the solid being made, here you probably can't visually see the water being made, but it is being made. So these are one of the things that you probably can't visually see sort of occurring, but it is occurring, and that's really why this reaction. And this again is our net ionic equation. And ultimately you could use like it's that very last H plus and the OH minus making water. This is also why these are sometimes referred to as acid-base neutralization reactions, because essentially you're making water in this case. And again, a double displacement reaction here at heart. Any questions on that there? Here's a couple other examples of some of these. I would say probably 99 times out of 100 will be soluble, but based on solubility rules, it is possible to get a salt that is insoluble, but I would say in most cases it will be soluble. So these are the salts here, and obviously these are our waters, these are our acids, and those are our bases underneath there. And same thing if we took this sort of combination here as our molecular equation, and we broke it apart into our total ionic equation, our nitric acid, which is a strong acid, would break apart completely. Our potassium hydroxide, also a strong base, would break apart completely. Once again, our water would stay together, and our potassium nitrate will break apart completely. And this would be our total ionic equation that's happening. And again, here, taking our spectator ions, which are exactly the same on both sides. And as I might have mentioned as well, they should be the same ions on both sides, and you should have the same number of those ions on each side. If you find yourself in this case where you do not have on each side. And as you can see here, once again, we hit the H plus from our nitric acid coming together. That's there to make our water formation. Any questions on there? Then if we did have a weak acid, say with a strong base or something like that. So let's just say we did take hydrofluoric acid, which again is a weak acid, and we did react it with sodium hydroxide, which is a strong base. Once again, positive, negative, positive, negative. That should tell you again, it is a double displacement reaction happening. We would then get a little H2O, which is our water, and a little NaF happening here. And again, that is from these guys switching partners basically here. And in this, our total ionic equation, because HF is a weak acid, which makes it a weak electrolyte, it actually will stay together and not break apart. Our sodium hydroxide will break apart because it's still a strong acid and strong electrolyte, which would break apart into Na plus and OH minus. Our water will stay together as it is a liquid, and our sodium fluoride is a strong electrolyte and break apart. Now, one of the different things that you end up with when you do throw a weak acid, even a weak base, a mix with a strong acid, is we actually will only get here one spectator ion, and the spectator ion in this case is actually the sodium ion. And that's because the HF is not completely breaking apart to produce that other spectator ion that's necessary. And our net ionic equation will actually still have the HF together and the hydroxide going to water and the fluoride here. So it will look a little bit different if you do have sort of a weak acid or weak base in the mix. You'll actually end up with just one spectator ion, and you'll still have that thing still together. I would say we probably won't come across too much of that, but just in case you do, that again is how you sort of handle anything that's a weak electrolyte. You basically just keep it together as you go through the total ionic equation. Any questions on double displacement reactions, ability, acid bases? Yeah. So we're going to then talk a little bit about the other sort of classification reactions, which is redox, and a little bit about sort of what's going on in a redox reaction. And then we'll talk about classifying things a little bit more specifically. Oxidation reduction reactions are pretty much what are referred to as redox reactions, and that does stand for oxidation and reduction. And oxidation and reduction occurs together. So one of the nice things about oxidation and reduction reactions or redox reactions is that if an oxidation occurs, a reduction has to occur with it. So they always happen together, which means, as we'll talk about, if you can sort of correctly identify at least one of those things, what is being oxidized, what is being reduced, by default, the opposite guy is doing the opposite thing. So that's kind of one of the nice things. If you kind of identify at least one of them, what's happening, you can identify what's happening in the other. The basic definition of oxidation that we pretty much will use in most general chemistry classes involves electrons and is the loss of electrons. And this is obviously electrons being transferred is the idea here. And the reduction is somebody that will gain electrons. So once again, the redox reactions account for our transfer of electrons. And that again is one of the three reasons why a reaction takes place. Some people remember this as Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig, oxidizing is losing, reducing is gaining, whichever way you like, I suppose. There are a couple other definitions of oxidation and reduction that we'll see in just a sec, but for the most part, we don't really use it too much here in general chemistry. Organic chemistry, where there's a lot of non-metal sort of with one another. So if you want to look at our state far into oxidation numbers, so for our purposes, for the most part, you could kind of think of oxidation numbers as stated as like the charges of each of these elements have on each side of the arrow. It's not exactly the same thing like that. To remember is in terms of like an oxidation number, our charge is if you have anything from the periodic table by itself, not combined with anything else, and that includes also our diatomic molecules like hydrogen, oxygen, nitrogen, that's how they normally come. They pretty much figure out what is happening in terms of who's being who's being reduced by using a very simple number line type of deal. And on a number line, to the right of zero is usually positive numbers. To the left of zero, there's negative numbers. Now, when I lose electrons and go through oxidation, will I become more positive or more negative? What do you think? 50-50 shot. So if I lose electrons, we're going to become more positive, right? Because we have more protons than electrons at that point, right? So we're going to become more positive. So if you look at really the oxidation state of an element on the left-hand side of the arrow and to the right-hand side of the arrow, and that oxidation state is kind of moving in this direction on the number line, that is becoming more positive, and that thing is going through oxidation. Now, when you gain electrons, you become more negative because now you have more electrons than protons. And if you look on the number line and you're moving in the more negative direction, that substance is going through reduction. So for example, if I take zinc, like that experiment you did before, and I react it with a little hydrochloric acid, gonna give me some zinc chloride and some hydrogen gas in this case. And I'll balance it like I'm a chemistry class, and maybe I'll balance it better than I did there and put the two in the right spot. There you go. That should do it, I think. Now, when we look at all the elements that we put on here, when we look at the zinc on the left-hand side, that is zinc just by itself. It has no charge. It has a zero oxidation state. Remember, things really only get charges when they come together. Metals and nonmetals, that's when things get positive and negative charges. By themselves, they have no charge. They have no oxidation state. Hydrogen chloride or hydrochloric acid is +1 and -1. On the right-hand side, our zinc is now hooked up with the chloride, and now it will have its normal charge of +2, and chloride, it would be -1. And now we have the hydrogen all by itself, which means that is naturally how it comes uncombined, would have a zero oxidation state. First off, any questions on assigning those things there? So this is how the number line works. If you like to use it, you draw your number line, and we look at something like zinc to start with. So zinc is starting at 0 on the left-hand side, and as it goes to the right-hand side, it is heading towards +2, which means it's going in the positive direction. That means in this case, zinc is being oxidized. Now, if we look at the hydrogen on the left-hand side, hydrogen on the left-hand side is +1, just like about there. And when it goes to the right-hand side, hydrogen is actually 0, which means it's actually moving in this direction, becoming more negative, which means the hydrogen here is actually being reduced or going through reduction. Chloride, is anything happening to the chloride? Left-hand side, it is -1. Right-hand side, it is -1, which means nothing is happening to the chloride in this case. Yeah. So in this case, it is just the zinc and the hydrogen that are exchanging electrons, really, in this case. Now, we could actually clean it up here, and we could do a total ionic equation for this. If I were to write a total ionic equation for this, it would be zinc plus my 2 H pluses from my hydrochloric acid and my 2 chlorides, going to my zinc with a +2 charge, my 2 chlorides, as that 2 comes to the front here, and my H2. And that would be my net ionic equation, my total ionic equation here. We just talked about really didn't change a spectator ion. So it's just floating around doing nothing in this case, which is why nothing happened with it. Now, really the net ionic equation in this case, which is the zinc plus our hydrogens here, going to zinc and our hydrogen gas in this case, right? And what's happening is this zinc is sending over a couple of electrons over to the H plus. When it does so, the H pluses will gain those electrons and become hydrogen gas and start to bubble out of solution. And the zinc will actually go for a swim into the solution. Any questions on that there? So once again, this is really a electrons being transferred is what is happening here. There's a net ionic equation there on the bottom. So you did this experiment with a really big piece of zinc, otherwise it would have completely disappeared. So if you did this and you had your H plus and your Cl minus from your hydrochloric acid, and you took your piece of solid zinc, what is really happening in this case when you did this is when you put that piece of zinc in there, the zinc's going to send over its electrons, and it is at that point the zinc will go from solid to the aqueous solution and have a charge and start floating around. And the H plus will gain those electrons and become hydrogen gas, which will then bubble out of your solution in this case. That's why if you took a really small piece of zinc, which I think in that experiment you did, they gave you the biggest piece of zinc known to man, which never will dissolve for a long, long time. But if you took a really small piece of zinc, it would actually disappear. And it's not really disappearing. It's those solid zinc ions losing electrons and actually jumping out of the solid state into the aqueous state and floating around. And again, those bubbles that you see are all the H pluses floating around, picking up those electrons and turning into hydrogen gas and bubbling out as solution. And that's essentially what's happening. Sodium chloride being formed. And if we look, this is no charge oxidation state, no charge oxidation state, as that is naturally how those guys come. When they do get together, that is when our sodium gets a +1 charge and our chloride gets a -1 charge. So once again, we could go to our number line here and see what's happening. If we look at the sodium, it starts at 0 and ends at +1, which means the sodium is going through oxidation in this case. And the chlorine here is starting at 0 and ending at -1, which means it is becoming more negative and going through reduction in this case. So once again, in this case, as it shows on the bottom, our sodium is sending electrons over to our chlorine here, and it's going to get reduced. That is a metal and a non-metal, right? What normally makes a positive charge? The metal or the non-metal? Who usually has the positive charge and is a cation? It is the metal. So when you have a metal and non-metal coming together in these reactions, the metal should always be the one being oxidized, right? Because it should always be the one losing electrons. The non-metals are always the ones gaining electrons, which means they should always be the ones being reduced. So it is super easy to figure out when you have a metal and non-metal together, what's being oxidized and what's being reduced, because the metal should always be the oxidized and the non-metal should always be the one reduced. Now, the little number line thing works well with that, as you can see. Good in a situation, say we had copper with a +1 charge on one side. Actually, we'll do a +2 charge. And to copper with a +1 charge on this case. It is being reduced. So in this case, the copper is starting on the left-hand side at +2, which is here. And then going to +1, which is moving in this direction, right? Becoming more negative. It's not reduced in this case. So this is a nice thing. You can use that little number line, positive and positive on both sides. That's a good way to use it. Any questions on that there? So this is a redox reaction. Example redox reaction, which is magnesium and oxygen coming together. Magnesium is 0, oxygen is 0. Magnesium on this side is +2 and -2. Once again, here we know that the magnesium is a metal, oxygen is a non-metal. So we really should know that the magnesium is being oxidized. But in case you can't remember that and you can remember this, you could still do it. Magnesium starting at 0, ending at +2. So becoming more positive, being oxidized. The oxygen starting at 0 and becoming -2, becoming more negative, which is becoming reduced. So again, if you can't remember metal, non-metal, you could again use the number line to figure out what is being oxidized, what is being reduced. Ultimately, in this case, what we're having is those electrons being transferred over to the oxygen in this case. Now, sometimes we do break apart a reaction like this, and we won't probably do too much of it at all in this class, but sometimes you'll hear about half reactions when you talk about redox reactions. And one half reaction is what is known as the oxidation half reaction, and one is known as the reduction half reaction. The top one here is the oxidation half reaction. And that is because it shows the magnesium losing electrons. And in an oxidation half reaction, the electrons will always end up on the product side, like they're being given off. So here's like magnesium giving off these electrons. And that is different than the second one, which is actually the reduction half reaction. And there we will find the electrons on the reactant side, like they are being gained. In this case, we have 4 electrons because each magnesium will lose 2 electrons, and there's 2 of them in the balance equation. So that is where the 4 electrons come from. And here, each of these oxygens, these 2 oxygens, each will gain 2 electrons to become -2 charges each, and that's where the 4 electrons end up. That is why electrons should always cancel, because however many electrons somebody loses in the oxidation part of the reaction should be the same number of electrons somebody gains in the reduction part of the reaction. So it should be like a perfect transfer of electrons from one guy to the next in a redox reaction. They are really called a half reaction because when you add them together, the electrons cancel and you'll get the overall reaction back, basically. So they of the reaction that are taking place. Any questions on that there? Now, as I mentioned before, we're not going to deal too much with the other sort of definitions, but a lot of times, especially in organic chemistry, when you get there, a lot of times we look at oxidation and reduction a little bit differently. And just to give you the sort of idea of what that is, when we look at the oxidation, which is obviously a loss of electrons, it could also mean a gaining of oxygen as you go from reactants to products. It could also mean that you lose hydrogen as you go from reactants to products. So those are two other sort of definitions of oxidation that are sometimes used. And again, a lot of times in organic chemistry with nonmetals, reduction also has similar definitions: the loss of oxygen as you go from reactants to products, and the gaining of hydrogen as you go from reactants to products. So a lot of times when you're dealing with nonmetals, there's not a lot of charges, not a lot of metals happening there. So we could look at something like sulfur here, has some oxygen, gains a little bit more oxygen, so it is being oxidized as it gained oxygen as it went from left to right. Here, the oxygen sort of disappeared, which means it has less oxygen, and the oxygen here would be reduced. So I wouldn't worry too much about those definitions, probably until you get closer to organic. But definitely in the gaining and losing of electrons, we use a lot in general chemistry in terms of the definition of oxidation and reduction. All right, so as I mentioned before, these are the three reasons why a reaction takes place. And as we've just been talking about, and we'll see one more time here, that is our double displacement reactions, which takes care of the first two. And our redox reactions basically take care of the one there. So now that we have these sort of big umbrellas of classification, we can get into some more specific classifications of these reactions, which fall under these sort of big umbrellas. And let's start with our double displacement one more time. So a precipitation reaction is a more specific classification of a double displacement reaction happening. And this is a positive, negative, positive, negative. And these guys switch places to the other side. The formation here of a solid, which is our precipitate, means that can be classified probably by most people as a precipitation reaction. It is still really a double displacement reaction that is happening in this particular case. Now, this guy here, where we have something like K2CrO4 and BaNO3. Just a reminder about a couple of things we've been talking about in these last couple of chapters. If you are given this equation, on the other side of the equation, you want to make sure that you do start with just the formulas, correct formulas, and then you should do the balancing. So you could definitely recognize this as an ionic compound. So two positive and negative guys, we know they're going to switch partners. When you're going to do that and predict what's on the other side, you want to think about what is just the basic unit of ions that make this guy up. So that is potassium, which is group 1, has a +1 charge. That is chromate, which has a -2 charge. Barium here is barium group 2 +2. That is nitrate, which is -1. These 4 ions are the basic ions that make up these compounds. When they switch around ions, they should come together properly, which, like we talked about with naming, means balance out the charge the simplest way possible. That is why when we switch these ions like this, we are essentially putting together K plus and NO3 minus, which is +1 and -1. And that is why what you saw on the screen there was KNO3, one of each of them, not like K2NO3 2 or anything weird like that. Now, when we put together our barium and our chromate, that is a +2 and a -2, which means when we put it together properly, we get a BaCrO4, one of each of them. It is at this point where you get the proper formulas down. Now you could go back and balance it if it's not balanced. And this is why the coefficient here is actually in the front. And again, not wrong formulas like K2, NO32. So again, sometimes people will try to balance and write the formulas at the same time. And as we talked about, you do not want to do that. Otherwise, again, you will get the wrong equation and the wrong formulas. Any questions on that? Obviously, we could still use our solubility rules here. Potassium's group 1, so that's going to be aqueous. Nitrate, soluble in everything. Potassium soluble in everything. And this guy would be our solid in this case. And again, why it's a precipitation reaction. If you went through the actual total ionic equation, net ionic equation, you would end up with this as your net ionic equation, which is the barium from the barium nitrate. We'll go find the chromate from the potassium chromate, and those guys will make a solid barium chromate, which is our net ionic equation. Any questions on that there? So that's a really good reminder. Again, sometimes people want to kind of do both of those things at the same time, and you definitely do not want to do both of those things at the same time. Any questions on that there? How did, as we've been talking about how you recognize these things, there is no other reaction you'll come across that has two ionic compounds to start out with. So as soon as you see two ionic compounds, automatically think double displacement, should automatically think just switch partners. The only one that will have sort of that setup to begin with, two ionic compounds coming together. This is our acid-base neutralization reaction, which once again is a positive negative guy. Instead of a solid being formed here, this double displacement will give us water being formed. And that again is one of the reasons why it takes place. So instead of a displacement reaction, most people will classify this as an acid-base neutralization reaction. As we talked about a little bit earlier, pretty much your main reaction is going to be the formation of water in this case. Any questions on that there? All right, so here is some redox category. So we're going to switch over here and talk about some more specific ways to classify redox reactions. So as we saw earlier, this again is a redox reaction. This top one, we have 0 in terms of oxidation state, 0, +1, -1. To -1, becoming more negative and being reduced. So oxidized and reduced, which again is what we would expect, as we've been talking about, since that is our metal combination. This reaction is one that we've seen before. This is actually a replacement reaction. And in a single replacement reaction, what is happening here is one of two things. We will start with one thing plus another thing, and this guy is an ionic compound. This could be a metal that has no charge by itself. And if this is a metal with no charge, it will come in and kick out the positive guy. And when it does so, it will then gain a charge and make a new ionic compound. The positive guy will come out and end up with no charge. You could also do this single replacement reaction with a nonmetal. And you did this probably in your experiment. This is the one with all the halogens and the reactivity and the heptane and the different layers and colors going from the top layer to the bottom layer and all that kind of stuff. Probably smelled really bad. Did you guys do that individually? Yes. Your desk, yeah. Smelled really bad perhaps as well. Also a positive negative. Our nonmetal by itself has no charge. It will actually, though, kick out the negative guy because nonmetals make negative charges, and it will make a new ionic compound, and our negative guy will come out with no charge. And that is what we see here. Our zinc is coming in, kicking out the hydrogen. When it does so, hydrogen will come out as hydrogen gas in this case. This has no charge, +1, -1, no charge, +2, -1. As we did that one earlier here, that is all a redox reaction, right? Our zinc is being raised, our H plus here is being reduced, as we talked about earlier on in a few slides back. If you remember, the deal is the guy coming in needs to be more or less reactive than one it's replacing for this reaction to work. The guy coming in needs to be more reactive than what it's replacing. So the guy coming in, A, be it a metal or non-metal, needs to be more reactive than what it is replacing. If it is not more reactive, the reaction will not take place. So if you remember from that lab, the halogens, group 7 on the periodic table, fluorine, chlorine, bromine, iodine, reactivity increase which way? Heading towards fluorine or heading towards iodine? Yeah, reactivity increase this way, right? That's because in that experiment, what you should have saw was the chlorine had no problem replacing the bromine. The bromine had no problem replacing the iodide, and the iodine couldn't replace anybody. And that means that the reactivity increases as you go upwards. And that is what you can use as what's referred to sometimes as an activity series. Activity series is a list of elements, and things higher on the list is more reactive than lower on the list, and they'll replace each other. Things lower on the list is less reactive than anybody higher on the list, and they won't replace each other. For metals, a lot of times you'll have a bunch of elements listed, hydrogen somewhere in the middle-ish, and some more elements. So in an activity series like this, for example, you may have zinc this way, you may have copper this way. In this case, copper is higher on the list than hydrogen, which means that reaction will take place like you did when you put your thumb on it with the zinc and the HCl. If you try to do that reaction with copper and HCl, it would not take place. And that's because copper is less reactive, so the reaction would not take place. So this is how you could recognize a single replacement reaction. You'll have a metal by itself. Typically, you'll have a non-metal by itself, and you'll have one ionic compound. So that is, again, different than double displacement where you have two ionic compounds. Here you have one ionic compound, a metal or a non-metal by itself. And that is how you could kind of recognize that it's going to do this sort of single replacement reaction. So a single replacement reaction, once again, is a more specific classification of really a redox reaction that's happening here in this case. Basically, transferring of electrons is what's occurring. The next reaction classification is a combustion reaction, and this also falls under the redox category. Now, I would say probably 99 times out of 100, tell me what a combustion reaction is. This is probably the combustion reaction they want you to tell them, which is really an organic combustion. And an organic combustion means you take something that's an organic compound like this, which typically contains carbon, hydrogen, and oxygen. You typically will have O2 in this case. CO in water, but most of the time it's going to be CO2 in water. That is basically what happens when you light your Bunsen burner, right? You get a little flame, a little spark, and that is a combustion reaction. Propane, butane, a lot of those organic guys are very, very combustible and will make fire and stuff like that. So like I said, that's probably in most cases what somebody would want in a combustion reaction if they ask you what that is. The true definition, though, of a combustion reaction is pretty much a lot simpler. In order for it to be a combustion reaction, pretty much you just need O2 present. So just the presence of O2, technically speaking, is a combustion reaction. So any reaction that has O2 on the left technically is a combustion reaction, but as I mentioned before, probably in most cases, the bottom ones there, probably people are looking for. Any questions on that there? Classification of redox. The next more specific classification of a redox reaction is a synthesis or combustion reaction, which once again is a redox reaction. Synthesis or combination reaction is pretty much what the name sounds like. You take two things and you make one thing. Yeah, so two things make one thing. That's how you recognize it as a synthesis or combination reaction. So here we have water, or H2, and oxygen. Two things make one thing for water, synthesis reaction or combination. Sodium, chlorine coming together, two things make one thing, synthesis or combination reaction. Now, to demonstrate the idea that you can classify the same reaction a few different ways, we take this guy here, magnesium and oxygen that we saw earlier, magnesium oxide. That is a redox reaction, as we talked about. That to me looks like two things to make one thing, yes, which is a combination reaction. And dare I say for the trifecta here, that is oxygen, which means technically it could be a combustion reaction. So there are multiple ways that you could classify the same reaction depending on what you're looking for. I would say probably most people would classify this as a synthesis or combination reaction. But again, it could be classified as a combustion reaction because it has that oxygen component, and it's definitely a redox reaction, as we talked about. So again, there are multiple ways to sort of classify the same reaction, and it does happen sometimes. My advice would be to pick the best choice for the situation of your options as to what you're looking at. Now, the last sort of classification here of reactions is a decomposition reaction. And a decomposition reaction is pretty much the reverse of a synthesis or combination reaction. It's kind of where you take one thing and you break it apart into a couple of things. So kind of like the opposite approach there to putting it together. So synthesis is like putting it together. Decomposition is like breaking it apart. And here we have water. If you run an electrical current over it, you'll get some hydrogen gas and oxygen gas. This is also a redox reaction. That is +1, -2, 0, and 0 in this case. So when we look at this reaction, this is +1, -2, 0, and 0. In this particular case, we start with water and we break it apart into hydrogen gas and oxygen gas. Still a redox reaction, but in this reaction, what is being oxidized? Let's see. Let's take a look at the hydrogen first, right? Hydrogen is starting at +1 in this case, ending at 0, which means the hydrogen in this case is actually being reduced. Yes, becoming more negative. The oxygen, which is -2, which is here, is ending at 0, which is actually becoming more positive and being oxidized. So in this kind of reverse reaction of breaking water apart, it's actually reverse of what happens when you put water together, which is this. H2O2, 2H2O, 0, 0, +1, -2. In this case, the hydrogen is going from 0 to +1 and is being oxidized. And the oxygen is going from 0 to -2, it is being reduced. So when you do go opposite, the opposite things that happen in this case. In the case of making water, which is a synthesis reaction on the left, it is the hydrogen that is losing the electrons. But when you go the backwards and do electrolysis, it's the opposite. It is the hydrogen actually gaining electrons, going backwards. It got to get its electrons back. So that's how you know these are really just opposites of each other. A synthesis and a decomposition reaction, because going one way when you put together, the hydrogen gets those electrons back to remake it back to where it started from. So they're definitely reverses of each other in that particular. Any questions on that? So finish up here. What we have kind of two big. Once again, is our AB. This big category falls precipitation reactions, more specific classification, and acid-base neutralization reactions. Which accounts for, again, water being formed and a solid being formed, which again are two of the three reasons to take place. There is no misunderstanding, no electrons being transferred in a double displacement reaction. So there's no electrons going anywhere in a double displacement reaction. They have the same charge on the left-hand side and the right-hand side in a double displacement reaction. So no transferring of electrons happening in either a precipitation, acid-base reaction, both of which are double displacement reactions. Now our redox category, which is all about transferring of electrons, under there we have our synthesis reaction, which is two things make one. We have our decomposition reaction, which is one thing makes two things or more. We have our single replacement reaction, which is one thing plus an ionic compound, where it comes in. And we have our combustion reaction. And again, those are more specific classifications of a broader classification of redox. Any questions on any of those classifications? All right, that chapter 7, I think.